Alright, so for oral homework 6, I was assigned problems 3, A through F for the modular arithmetic section. So this is all going to be testing the congruence of different statements. So for example, A here is 9,875 is congruent to 3,594 mod 3. So I was using two major methods of testing congruence mostly for these problems, which the first description of it is definition 5.4.1 from Zybook, which is x is congruent to y mod m if x mod m is equal to y mod m. So for the first one here, for A, 9,875 mod 3 brings back a remainder of 2, and 3,594 mod 3 brings back 0. So because those are obviously not, 2 is not equal to 0, by definition of 5.4.1, that statement is false for A. For B, the statement is 5,660 is congruent to 1,642 mod 7. So the other way of describing congruence, or testing for congruence from the Zybooks, is x is congruent to y mod m if and only if m divides x minus y. So for this problem, I tested this out. Does 7 divide 5,660 minus 1,642? So does 7 divide 4,018? And that answer is yes, and it brings back a value of 574. So because 7 divides x minus y, therefore this statement is true. It is a congruent statement, so true. For C, the statement was an integer k is congruent to an integer k modulo m. I think the distinction is assume all variables represent positive integers. So k would be congruent to k mod m if and only if k mod m is equal to, because how this is structured, k mod m. So since k mod m and k mod m are the same expression, I would assume they're congruent, and because this is a congruent statement, it is true for C. For D, the statement is a minus k times m is congruent to a modulo m. And I was stuck on this one for a little bit before I tried assigning a minus k times m to another variable, x. So that follows that x would be congruent to a mod m if and only if m divides x minus a, by definition of this second test for congruence. So I substituted a minus km back in for x here, and that left me with the statement m divides negative k times m. So by the definition of division from 5.1 in the Zybook, x divides y if there's an integer k such that y equals k times x. Therefore, m dividing negative k times m is true, as negative k times m will always maintain divisibility by m, the same way that 2 is always going to divide 2 times k, because 2 times k is always going to still be divisible by 2, because, again, just the way that division works. So therefore, the statement a minus k times m is congruent to a mod m. So that's true. For E, the statement is a is congruent to 0 mod k times a. So by the testing for congruence here, a mod k times a would have to be equal to 0 mod k times a. And for the modulo functions, since 0 mod basically any number, it's always going to return 0 as that number. So the statement is false because a mod k times a, since a is a positive integer, that will return a regardless of k's value. And because a, or any positive integer, is not equal to 0, therefore a is not congruent to 0 mod k times a. So that is a false statement. And for f, the last one, the statement is if a is congruent to b mod k times m, then a will be congruent to b mod m. So I just listed out some examples because I wasn't really sure where to start. I started with a true congruent statement from earlier problem 3b here. So 5,660 is congruent to 1642 mod 7. And then I just tried to kind of plug this into what the statement was saying. So if a is congruent to b mod k times m. So a would be 5,660 in this case, b 1642, m would be 7. And so I'm testing out different values of k. So putting in 2 for k brings back yet another true statement. However, putting in 3, 4, and as the numbers go on, those bring back false congruence. So since k times m manipulates the modulo operation, it changes the output of that operation by manipulating m with the integer k. And because k is manipulating it, therefore it completely changes the output of that operation. Maybe that doesn't make sense in words, or I'm just scrambling them, but I had another example here to kind of describe this. So if you had an operation, like the second one here, a is congruent to b mod m, or b mod m, where m equals k times m, 21 mod 2 is different than 21 mod 3 times 2, or it'd be different than, any integer you're multiplying by 2 that completely changes the modulo operation and brings back something else. It doesn't really denote any equivalence with the entire operation. So since this first statement is false in this if-then statement, k times m is not equal to m, and basically creates an entirely different operation. So you can't derive that this if-then statement to be true, because simply b mod m is not going to be the same than b mod k times m in any regard, because having m being manipulated by an integer k changes the output of that operation entirely, and because it would change that, it changes how you would test for congruence between these two different statements, and naturally they'd likely bring back different congruence depending on the values.